Hello, Royals. Let's talk about 6.1 and vector concepts. I'm going to go all the way to the end of the lesson and take a look at this parallelepiped. And in this parallelepiped, we should get lots of opportunity to talk about other concepts. Now, this is supposed to be a parallelepiped. You'll have to trust me on that. Each face being a parallelogram. A cube is an example of a parallelepiped. A rectangular base prism is an example of a parallelepiped, but you don't need congruent edges, and you don't need perpendicular edges either. Okay. So in this parallelepiped, notice it is labeled in cyclic order. We'll talk about that cyclic order for even just parallelograms here. I've decided to label this vertex A, and then I decide to label this vertex B. I now have two choices. Actually, for the parallelepiped, let's start again. I start with A here. I could choose to make vertex be this vertex or this vertex or this vertex. I have three choices. When I choose this vertex to be B, I'm going to have two choices for which vertex is going to be C. In cyclic order, I could label that vertex C. I decide not to and label this vertex C. And now I have no more choices. In cyclic order, going around on this face, these two vectors define a face, A to B and then B to C. D must complete that face, that parallelogram. So here is the parallelogram A, B, C, D labeled in cyclic order. Okay. I also don't have any choice about where vertex E goes. Once I complete one face, the next four letters in alphabetic order, in cyclic order, have to correspond with the first vertex that I labeled. Think of A is to E as B is to F, as C is to G, as D is to H, kind of thing, like an analogy. So I label this A, that B, that C, that D, this E, F, G, H, and there's a parallelepiped labeled in cyclic order. Okay. In the parallelepiped, the definition that, and this is sometimes a surprise for students, even physics students, that the definition of a vector is independent of its position. So the vector AB is equal to the vector EF. They are equivalent vectors. They are equal in direction and equal in magnitude. Therefore, they are equal. Other equivalent vectors to AB are DC and HG. Even just in the parallelogram, if I label the vector AD, that has to be equivalent to the vector BC. And this is where the cyclic order is so important. So I'm going to just do a new parallelogram with you. I wonder if I can fit it in the same time. I'll try. And show you that it doesn't matter how I draw the parallelogram, as long as it's in cyclic order, the vector AB will always be equal to the vector DC. So I don't know, let me try a parallelogram that looks like this right here. And let me say, I'm going to start A there. Let's see, I did that one clockwise. I'll do this one counterclockwise. So I'll go A, B, C, D. Notice in this parallelepiped that the vector AB is equal to the vector DC. They are equal in magnitude and direction. AB is the opposite of DC, which is, or sorry, the opposite of AB is equal to the opposite of DC, which is the vector CD. Let's check that in this diagram. Where's the vector AB? There's the vector AB. And it is equal in magnitude and direction to the vector DC. This is why cyclic order is so important. Okay, that should come up a couple of times in your homework, so make sure you're ready for that.